Hello all. In the previous two sessions we have discussed about the binary numbers and then we have discussed about the conversion from one number system to the other number system. And as I said in the previous session, in today's class we will be learning about complements. Complements is very important in digital electronics because this is used to simplify the subtraction operation and it is used in many of the digital circuits. In digital electronics, usually what we do is we are going to implement or we are going to represent subtraction as 2's complement addition. Using the adder circuit itself we can represent subtraction also, we can obtain subtraction also. So how it is done? So if you find the 2's complement of the second operand and add it to the first operand, then so that will be equal to the sum that will be equal to the subtraction of the first and the second operand. Therefore, so instead of using another separate hardware for the subtraction operation, what we can do is we can use some additional gates, using additional logic we can realize the subtractor using adder circuitry. So that is the advantage we have. Now let us learn, so what are complements, what are the different types of complements we have, and then let us learn so how to perform subtraction using complements. Okay. Yes. Now if you consider complements, there are two types of complements. The first one is diminished radix complements. Second one is radix complement. These are the two types of complements we have. Now let us see what is diminished and what is radix complement in detail and how to perform, how to obtain the diminished radix complement and radix complement. Now as an example, if you consider the base, if the base is equal to 10, if you consider the decimal number system, then you can see this diminished radix complement is nothing but r minus 1, we represent it as r minus 1's complement. R minus 1 is nothing but 10 minus 1, which is nothing but 9's complement. 9's complement. Next, if the base is 2, if r is equal to 2, then then r minus 1 is the diminished, that is r is 2, 2 minus 1 is 1. So diminished complement in binary is called as 1's complement. Next, if you consider the radix complement, this is diminished radix. So if you consider radix complement, then the base is 10. If r is equal to 10 in case of radix complement, then it is represented as r's complement, which is nothing but 10's complement. And if the base is 2, then it is represented as r's complement again. So r's in the sense 2's complement. Therefore, so in today's class we will be learning about the r's complement and r minus 1's complement, or so in other words 10's complement, 2's complement and 9's complement and 1's complement. These are the four different types of complements we are going to learn today. Now let me consider diminished radix complement, so which is nothing but for decimal it is 9's and for binary it is 1's complement. Yes, let me consider first one, diminished radix complement. Yes. Now, so we have a formula here. So let us see. So what is the formula in order to convert, that is in order to obtain 9's complement and 1's complement. This is diminished, therefore we need to consider r minus 1's complement. So now, so the generalized formula here what we have is r to the power n minus 1, so diminished, and so we need to subtract So n from this r to the power n minus 1. Now let us see what is this r, what is this n, and what is this capital N. So now if you consider, okay, so now the r what we have here is base or the radix. N is nothing but number of digits in capital N, okay, number of digits in capital N. Therefore, what is n? N is nothing but the given number, okay, for which we need to obtain the complement, any of the complement, okay. So, a given number. Yes. Now, so let us, okay, see how to obtain 9's and 1's complement. So, now let us consider an example, okay, obtain 9's complement of, okay, let me consider any, okay, number. So, I have taken 72,436, okay. So, let us consider, this is the problem given. Then, okay, let us see. So, how to obtain 9's complement of a number. So, r to the power n, what is r here? So, since we have number given in decimal number system, so r base is 10, okay. So, small n is nothing but number of digits in the given number. How many digits are there? 5 digits are there. So, 10 power 5 minus 1, okay, minus the number is 72436, okay. Yes. So, 10 power 5 minus 1. So, what is 10 power 5 minus 1? 10 power 5 is, okay, we need to write 10 power 5 first, subtract 1, then later subtract 72436. Okay. Yes, this is 99,999 minus 72436. So, if you subtract, so what we are going to get? 9 minus 6 is 3, again 9 minus 3 is 6, next 9 minus 4 is 5, next 9 minus 2 is 7, 9 minus 7 is 2. See, this is the 9's complement of the given number. So, 27,563 is 9's complement of 72,436, okay. And now let me consider another example, but I am going to consider second example in binary, because we have learned, so how to obtain 9's complement. Now we need to understand how to obtain 1's complement, okay. So let us consider the question as obtain 1's complement of 10110. Let me consider, this is the given sequence, okay. Yes. Now in 1's complement, okay, so what we are supposed to do? We are supposed to use the same equation here, okay. Let us use the same equation. So how many digits are there? Small n, before that base is 2, r is 2, okay, small n is 5 and capital N is 10110, okay. Yes. Now let us use the formula, okay, later I will tell you very simple method. Now let us use the formula and let us obtain what is the 1's complement of the given string. Yes, now 2 to the power 5, 2 to the power 5 minus 1 minus 10110, okay, 110, yes. So 2 to the power 5 is 1, okay. So 32 we need to represent. So 32, yes, 2 power 5, other bits are 0. This is the representation for 32 in binary, and yes, so minus 1, next 10110. Yes. Now what is the result of subtraction from 32? Okay, from 32 we need to subtract 1. So what is the result? So we are going to get 31. 31 is nothing but, okay, all 5 bits ones minus this. So now let us see the subtraction. Yes, subtraction, 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 1 is 0, 1 minus 0 is 1, 1 minus 1 is 0. Yes. Now, so this is the ones complement of the given number. Now, if you compare the result what we have obtained and the given string, you can, okay, so identify a very easy method for finding ones complement. We need not have to, okay, go use this formula, okay, use this procedure to find out the answer. Instead, if you compare these two, so you can find out a very easy method. That is, if you just observe for the last bit, okay, we have 0, here we have 1, here 1, 0, 1, 0, 0, 1, 1, 0. So what is the easiest method? So from this what we can observe, if you observe carefully, the bits, okay, are just negated in the given string, whatever the string we have. So if you just negate the bits, that is sufficient to obtain the ones complement. That is the easiest, okay. So way to obtain the ones complement. So just use a not operation, that is negate the given bits. So then you will get, just make ones into zeros, represent ones as zeros and zeros as ones, that is sufficient, okay. Therefore, if I give some other example, okay, let us consider so let me consider this string. So if I ask you to obtain the ones complement, so ones complement of this is 0, 1, 0, 1, 0, 1, 0, 0. Yes, simply you need to, okay, so put zeros for ones, ones for zeros. That is the procedure, okay. Yes, so this is about diminished radix complement, okay. Now let us move on to the second one. So I need to consider, okay, one more example for diminished radix. Later I will explain, okay, by considering one more example. Now let us consider, okay, let us move on to the next type, and then we will discuss another example based on this. So second type is radix complement. Let us see how to find out radix complement. The difference between the diminished radix complement and radix complement is only one. That is, if you take the formula, so we will be having, okay, r power n as it is, but this minus 1 whatever we have, so this will not be there. The formula for radix complement is r power n minus n, okay, r power n minus n. So now therefore, so if you compare the previous one and this one, the subtraction what we had done, that is minus 1 what we had done from the number, okay, r power n is not there. Therefore, so now we have 9's complement, so you can use the formula, or else, so if you have 9's complement, if you just add 1 to it, that is sufficient to obtain the 10's complement. And it is same for the binary case also. There, if you just add 1 to the 1's complement of a given sequence, that is going to give you 2's complement of a given sequence, okay. Yes, see here, so radix complement, let me change, okay, the question itself, obtain the 10's complement of 72436. Yes, what I said, so this minus 1 will not be there, you need not have to subtract, okay, 1 from this. So for the same sequence, if I consider, see, it's 27,564. What was the previous answer? 27,563. Therefore, 2's complement in case of binary, 10's complement in case of decimal can be realized as, see, if it is 10's complement, 9's complement plus 1. See, this is the 9's complement we have. 9's complement plus 1 will give you 10's complement. Okay, very simple. Or you can use the procedure 10 power 5, that is, so r to the power n minus n. So using that also you can obtain. Or if you have already obtained the 9's complement, then you can just add plus 1. Yes, now let us see in case of binary. Okay. So obtain 2's complement. I am changing the question here. obtain 2's complement of 1 0 1 1 0. So in this case, so again yes, this minus 1 is not there. Okay, we need not have to subtract minus 1. Yes, this is the answer. So earlier we had 0 1 0 1 0 plus 1 will make the last bit, okay, whatever 1 we have, that as 2. So I have represented the result as 0 1 0 1 0. This is the 2's complement of given sequence. Yes, so if you consider this one, this example, we have 1's complement already. So in order to obtain 2's complement, we need to add plus 1 to this. Yes, result result of this 2's complement 0 1 0 1 0 1 0 1. This is the 2's complement of this string. Okay. So this is the procedure we follow, and now as I said, I need to consider one more example for both 9's complement as well as 1's complement. So because if we have a 0 here, okay, so how do we need to consider? So if we have a 0 here, do we have to consider, and how to proceed with that? So that is one more example I need to consider. So I am going to consider that example and I am going to explain. So in such case what we are supposed to do, okay, how to obtain the 9's as well as 1's complement. Okay. Let us now understand the subtraction with complements. So as I said, complements are used in digital computers in order to simplify the subtraction operation. Now let us learn how to perform subtraction. Okay. So in order to understand how to perform subtraction, I have taken two examples here. Okay. Let us learn how to perform subtraction using 10's complement first. Later we will learn, okay, how to perform subtraction using 2's complement. Now using 10's complement, so I have taken an example, subtract, okay, let me complete this, subtract, okay, 72,532, okay, minus this, subtract 3,250 from 72,532. So this is the example I have taken. Later I have considered, so instead of, if I consider this as x and this as y, here I have x minus y, I need to find out there, so I need to find out y minus x. So now let us consider, okay, the subtraction using 10's complement. So what is the procedure? So 10's complement, in order to perform the subtraction, we need to take the 10's complement of the second operand and add it to the first operand, the sum whatever we are going to get. So that is, we need to discard the carry, okay, so we will see that later. So if you consider the sum, only the bits, okay, only the digits, so whichever we have on the output, that is sum output, we need to consider. So that is going to give you the difference between these two data. Now let us, okay, take the 10's complement of the second operand. Now one point you need to remember here is, so we have 5 digits here, so we need to consider 5 digits for the second operand also. So let us consider 5 digits. So therefore, so 10's complement, the procedure I will just write, okay. So first operand is x, okay. Second operand will be, instead of y, we need to consider 10's complement of y. So let us separately obtain the 10's complement. 10's complement of 03250 is, what is the procedure? R power n minus n. Therefore, R power n is 5 digits we have, 10 power 5 minus 3250. Therefore, so if you subtract this, you will get this, okay, answer for this as 9, okay, then, so let me, okay, expand. So this is, yes, we need to add one more 0, 3250. Yes, subtraction, if you observe, so 0 minus 0, next we have, okay, here we have 10 minus 5, 10 minus 5 is 5, next we have 9 minus 2, 9 minus 2 is 7, next we have 9 minus okay, 3, that is 6. So this is the answer. Okay, this is the 9's complement of 3250. Okay, let us consider that. So 96,750. So you need to add these two. So addition will result, okay, sum or add. So 2, 8, 12, 9, 16. Okay. Now if you observe, we have, okay, end around carry. So we need to discard end around carry. So in order to discard end around carry, subtract, okay, just subtract, or you simply, okay, omit it and write the other 5 digits as the result. So if you subtract, what is the answer you are going to get? 69,282. So this is the answer for x minus y. Okay. So subtraction of this, that is 3250 from this, if you do, so this is the answer we are going to get. So this is the tens complement. Using tens complement, this is the procedure. Okay. Now let us see the next subtraction, that is y minus x. So in this case, so if this is x, this is y, so I have considered y minus x because there we are going to get result which is, okay, a negative result. So in tens complement, how it will be, okay, considered. So that is what we are supposed to understand here. Yes, now if I consider this 3250 minus this, yes, let us write as we did in the previous case, x is 03250, and next we need to consider tens complement of y. So that is the second operand. Yes, what is the tens complement of this? So we have 5 digits in the sense, so 1 0 0 0 0 0, okay, so minus 72532. What is the answer? 10 minus 2, 8. Next we have 6 minus 3, 9 minus 3 is 6. Next we have 9 minus, okay, 5. Next we have 9 minus 2. 9 minus 2 is 7. Yes. So 27,468. Let us, okay, write here. Yes, we need to add these two. 8, 11, 7, 10. Yes. So there is no end around carry. Okay. There is no end around carry. So you need to remember answer is negative. So answer for this case is minus tens complement of, so minus tens complement of 30,780. Let us find out what is tens complement, then we will put negative sign in front of it. Yes, so tens complement, what is the procedure? We have 5 digits here, so let us consider 10 power 5 minus 30,718 2, okay, next 9 minus 1 82, next 2, okay, next we have 9 minus 0 9, okay, next we have 9 minus 3, 9 minus 3 is 6. So answer is minus 69,282. Yes, you can observe here. So here if you do x minus y, we have plus 69,282. If you do perform y minus x, okay, then we are getting minus 69,282. Okay. Yes, this is the procedure we follow using tens complement. In a similar way, we need to understand how to obtain the subtraction using 2's complement. Let us, okay, learn that by considering 2 examples. Now let us consider one example for understanding how to perform subtraction using 2's complement. Okay. Yes, now we have, see here we have x minus y as well as y minus x. Let us consider, okay, x minus y first. Later we will find out what is y minus x. So first let me consider x minus 1. So yes, what is the procedure? First we need to consider first operand as it is 1 0, 1 0, 1 double 0. Next we need to consider the second operand, but it should be in 2's complement format. Okay, 2's complement of y. Yes, so we need to consider 2's complement of this. What is the 2's complement? First let us write 1's complement 0, 111, 00 plus 1 will give you 2's complement of the second operand. 2's complement of the second operand 0, 111. Yes, see here we have, so 3, okay, 5 plus 7, 2, sorry. See here we have 7 digits, here we have 6 digits. So we need to consider, okay, 7 digits in this case also. Therefore, so let us, okay, write this as 0 1 0 0 0 1 1. So for this 1's complement will be 1 0, okay, 1 1 1 0 0. So adding 1 will give you the 2's complement. 2's complement is 1 0 111 0 1. Okay. Yes, let me consider that. So data here 1 0 111 0 1. Let us add these two. We have 1 0 1 plus 1 2. Okay, carry 1. Next 1 plus 1 2 0, carry 1, 111 is 3, 1 1, 1 plus 1 is 0, okay, and at last we have carry as 1. So again we need to discard the end around carry. So discarding is nothing but subtract, okay, or just omit and write only the sum part of it. Yes, if you subtract this, okay, so this from this we will get 1 0 0 0 1 1 0. Yes. So if you want, you can cross check by converting these, okay, into decimal, because this is in the binary. If you have any doubts, you can convert and you can cross check. So this is equivalent to how many bits we have? So we have 7 bits, okay, 2 power 0, 2 power 6, 2 power 6 is 64, okay, then 2 power 5 is not there, 16, okay, plus 8 is not there, 4. So what is the, okay, sum of this? So we have 84, and on the other end we have 2 power 0, 1, 2, 3, 4, 5, 2 power 5 is 32, 32 plus 3 is 35. So we have 84 minus 35, 84 minus 35 is so 8 we have here, yes, 49. So do we have 49 here? That we need to check. Yes, 32, 32 plus 16, 32 plus 16 plus 1, yes. So we have 49. Okay, this is okay, one method for validating the result whatever we have. In today's class we will be learning about Boolean algebra and logic gates. Okay, so out of this let me consider Boolean algebra first. Boolean algebra, like any other mathematical system, so it is a set of elements, set of operators, okay, and so it will be consisting of number of unproved axioms or postulates. So if you consider set of elements, so any collection of objects which are having common property can be called as set of elements. So collection of objects having common property. Okay, so that can be considered as set of elements. And set of operators. So operators are the binary operator. So binary operator is an we can consider that as a rule, okay, which is applied on a pair of elements which are in the set. Okay, let us consider the set as S. So let us okay, define the binary operator as? Binary operator is a rule that is applied on a pair of each pair of elements of S. So, which is going to give another element, okay, which is in the same set S. So, that can be considered as the operators. Okay. Next we have postulates. Postulates in any mathematical system are the assumptions what we make. Those are the assumptions which will, okay, help us to derive the rules, theorems and properties of the system. Okay. Now let us see the postulates what we have in any algebraic system. So postulates includes closure, associative, commutative, identity, next is inverse, last one is distributive. Yes, these are the 6 postulates we have. Now let us see, okay, what are these postulates one by one. So closure, a set is said to be closed, okay. So with respect to a binary operator, so if the binary operator is applied on each pair of the set S, then if it results in an element, okay, which is a part of the set, which is an element of the set, then we say that binary operator is closed, okay, that set is, okay, closed with respect to the binary operator. So closure, as I said, if I consider a set of natural numbers, then the operator plus, okay, is said to be, okay, closed. So because 1 plus 3, if I consider 2 elements of the set, so 1 plus 3, the result whatever we are going to get, it is also the part of the set N, or it belongs to the set N. Therefore then the binary operator plus is said to be closed with respect to the set N. Okay, so that is with respect to the closure. Next is associative law. The binary operator star is said to be, okay, associative whenever we have x star y star z, okay, which is equal to x star y star z. So whenever we have such relation, then we say the operator star is associative. Then on a set, yes. Next is commutative law. Commutative law, okay, the binary operator star on a set S is said to be commutative if we have this, okay, relation, that is x star y is equal to y star x. If it satisfies this, then we say, okay, so it is commutative. Okay. Then identity, a set S is said to have an identity element if an element E such that x star E is equal to x, or E star x is also equal to x. Okay. Yes. Next we have inverse. So inverse property says that if a set has an identity element, then there will be some element y, okay, so which will result in x star y is equal to E. So whenever we have such, okay, so relation, then we say, so y is inverse of x. Okay. Now if I consider there are two operators star and dot, then the distributive law, okay, says that whenever we have, okay, the relation x star y dot z is equal to x star y dot x star z. Okay. So whenever we have such relation, then we can say that star is distributive over dot. The operators and postulates have the following meaning, in the sense plus indicates addition, Next we have dot indicates multiplication, and additive inverse is subtraction, multiplicative inverse is division, okay, and so additive identity element is 0, multiplicative identity element is 1, and the only distributive law possible is dot over plus. So that is, if you have A dot B plus C, then it can be written as A into B plus A into C. Okay. So this is the meaning of these postulates. Now let us see the different theorems what we have in Boolean algebra. Now let us see the basic theorems which are used in Boolean algebra. So here I have listed the postulates as well as the theorems which we commonly use. So here in the postulates, so if you consider the Boolean algebra, in Boolean algebra we have the first postulate as closure, and since the set contains only two elements and these two elements are closed with respect to the binary operator plus and dot, because when we apply plus or dot, the result whatever we are going to get 0 or 1 is 1. So this element is also a element of the same set. Therefore, so we do not consider, because by default the set is closed with respect to the binary operators plus and dot. Therefore, first postulate is not mentioned here, and second postulate what we have in the binary or Boolean algebra is identity. So here if you observe the additive identity what we have is 0, so x plus 0 is equal to x. So then the multiplicative identity what we have is 1. Okay. So this is the postulate 2 in Boolean algebra. Next is postulate 3. Postulate 3 is commutative. So commutative says x plus y is equal to y plus x. If it satisfies this, so then it is commutative, and the other version for this commutative is xy is equal to yx. Okay. And next postulate in case of Boolean algebra is distributive. So distributive is x into y plus z is equal to xy plus xz. The other version what we have is x plus yz is equal to x plus y into x plus z. Okay. Next the fifth postulate what we have is for the complement. So complement in the sense, so x plus x dash is equal to 1. So if you add the complement of a variable to the variable, then it is going to result in the identity element 1, and on the other side, so x dot x dash is equal to 0. And these are the 4 postulates we use. As I said, closure is by default the closure is applicable to the binary number system. And the last postulate what we have in case of the Boolean algebra is the elements are unique. The elements what we have in the set are unique. Since we have only two elements 0 and 1, and since 0 is not equal to 1, so the postulate 6 what we have is also satisfied by default. So these two are not considered. So only the 4 postulates we consider are 2, 3, 4 and 5. So next let us see the theorems what we have in case of Boolean algebra. So the theorem 1 says that x plus x is equal to x, and the other version what we have is x dot x is equal to x. So next theorem is x plus 1 is equal to 1 and x dot 0 is equal to 0. Third theorem is involution. So that says, so the complement of a complement is equal to the original signal. Okay. And theorem 4 is associative. So associative law, x plus y plus z can be equal to, is equal to x plus y plus z. If it satisfies this, then we say it is associative in nature. So the other version, the duality of that is x into y into z is equal to xy into z. Next we have De Morgan's theorem. So De Morgan's theorem states that the complement of sum of two variables is equal to the product of individual complements, product of individual complements. So the other version is, so the complement of a product is equal to the sum of individual complements. Okay, so that is the fifth theorem. Next is sixth theorem, which is called as absorption, and it is equal to, that is, it is given by x plus xy is equal to x. The other version is x into x plus y is equal to x. Now let us see the proof for these, okay, theorems. So if I consider theorem number 1, so theorem 1a, we have x plus x is equal to x. Let us consider the LHS. LHS what we have is x plus x, okay. So let us consider this. Now let me write this as 1 into x plus x, so which is equal to, or we can write this as x plus x into 1 also. So let me write x plus x as it is, and so for this I will write x plus x dash. If you observe, so 1 can be written as x plus x dash. From postulate 5 we have, okay, therefore we can write 1 as x plus x dash. Further, so this can be combined. So if you observe, we have postulate 4b, okay, so that is distributive law. From distributive law, so it is in the expanded form. We can write the compact form of this. So that is, so x, okay, plus in place of y we have x again, in place of z we have x dash. Therefore, so this further can be written as x plus, so x into x dash. If you, okay, look into the table, x into x dash is available here, it is equal to 0, and x plus 0 is nothing but x. So from the postulates, by taking the reference or with the aid of the postulates, we can prove that x plus x is equal to x. So this is the for the theorem 1. So if you consider the part B of the theorem 1, so in theorem 1 we have part B as x into x is equal to x. Similar to this we can prove. So let us consider x into x, okay. So let me consider x into x plus 0, okay, because we know that, so variable or 0 will result in the same variable. Therefore x dot x is equal to x dot x plus 0 is equal to x dot x. Now for this 0 I will write x into x dash. Now let us, okay, so consider the postulate 4. So we have xy plus xz format here, xy plus xz, so which can be written as x, okay, into y plus z. So whereas x plus x dash, where we have x plus x dash, yes, so here we have x plus x dash is equal to 1. Therefore this becomes x dot 1, which is equal to x. Therefore, so it is proved that the theorem 1 what we have, so is proved. So we can say x plus x is equal to x and x dot x is equal to x. So this is the proof for theorem 1. Now let us consider theorem 2. Theorem 2 is x plus 1 is equal to 1. Let me consider the LHS. So this can be written as x plus 1 into 1. Further, this can be written as x plus x dash from postulate 5, and so now it is in the expanded form. So using postulate 4b, we can write this as x plus 1 dot x dash, so which is nothing but x plus x dash. So x plus x dash from postulate 5a, it is 1. Therefore x plus 1 is equal to 1. By duality, the part B of theorem 2 can be written as x dot 0 is equal to 0. So in duality what do? We replace 1 by 0 and plus by dot and vice versa. Okay. So by duality we can write the part B of theorem 2. Now if you consider the involution, that is complement of symbol, then so it can be written like this. So if I consider x, okay, x dash, further x dash of, okay, dash, that is complement of a complement. So x, let us assume it is 0 1, okay, x dash will be 1 0, so complement of this will be 1 0. So therefore x dash of whole dash is equal to x. So this is for the theorem 3. Next we have associative. So in associative we have x plus of y plus z, which is equal to x plus y, okay, plus z. So let me consider 3 variables for that. So let me consider x, okay, x plus y and y plus z. Later let me consider x plus y plus z, and last y, x plus y plus z, okay. Let me consider x plus y plus z. So let me, okay, write the values for this. Okay, the possible combinations are 0 0 0 2 1 1 1. Now x or y is 0 0 1 1 1 1 1 1. Y or z is 0 1 1 1 0 1 1 1. Now x, okay, plus yz, x plus yz, x or, okay, yz if I consider. So first column entry is 0 1 1 1, okay. Next after 4 entries, so we have 0 or 1, so 1 1 1 1, and the last one x plus y plus z, okay, 0 0 first, okay, 0 or 0. Next we have 1 or 0 is 1, 1 or 0 is 1, 1 1, 1 or 1 is 1, 1 or 0 is 1, 1 1 1. So if you check the last 2 column entries, so we have, so which are equal. Therefore, so we can say that this is the proof for associative law. Okay. So we have seen the proof for the 4 theorems. Now let us consider the De Morgan theorem. So De Morgan theorem, we have considered this for 2 variables here. So let us consider 2 variables, and let us, okay, consider the first part of it. So similar associative law, I have shown only the proof for the part A. Part B can also be proved in the same way. Now let me consider, so first De Morgan's theorem, x plus, okay, yes. So now let us consider the possible combinations. Complement of x 1 1 0 0, complement of y 1 0 1 0, x or y is 0 1 1, x or y complement is 1 0 0, okay. Next we have add between these two, 1 and 1 is 1, all other combinations we will get 0. Therefore, the part A of the De Morgan's theorem is proved, okay. Next if you consider the part B, okay. So what do we have? We have xy, then we have xy whole dash, then we have x dash plus y dash. Let me consider 0 0 0 1 1 0 1 1. Next complement of x and complement of y, x into y 0, okay, since it is an AND operation. So we get 0 for all except for the last combination. Next we have xy dash is complement of this, so we get 1 1 0, and last one is OR between these two, is 1 1 1 0, okay. This is the proof for De Morgan's theorem, okay. Now let us consider the last theorem, theorem 6, okay. In this also we have 2 parts. So first one is theorem 6a, so which, okay, we have as x plus xy is equal to x, x plus xy is equal to x. Let us consider LHS. So in this, so we have this can be written as, if you consider okay the distributive law, this can be written as x plus x let us consider LHS. So in this we can take out x as common and we will get 1 plus y. So further 1 plus y, so 1 plus any variable will result in 1. So this can be written as x. If you consider part B, this is part A, 6 part, okay, 6 A, and now let us consider 6B, x plus xy, so is equal to x. So in this we can write this as x plus xy again. So if I multiply, then this can be further written as, because x into x, so x into x is x, okay, xy will, now if I take out x as common, 1 plus y is 1, so this can also be written as x. So these are the proof for the theorems what we use in Boolean algebra. So this is about the Boolean algebra, the postulates what we have in Boolean algebra, and theorems what we use in Boolean algebra. Okay. In the next class we will be learning about the logic gates, different logic operations. Thank you.